Hey there, man, Alejandro, and welcome back for day 293 of me doing Daily LeetCode Challenge with 1 year's worth of weekly contributions here on GitHub. So today's runs for May 5th, 2025. Without further ado, let's get straight into it. Okay, today we get LeetCode Medium problem 790, Domino and Tromino Tiling. Okay, you have two types of tiles, a 2x1 domino shape and a Tromino shape. You may rotate these shapes. Okay, Tromino tile, I see, it's 3, so it's not like a quad domino tile. Given an integer n, return the number of ways to tile a 2x n board. Oh no, another counting problem. Since the answer may be very large, return a modulo. Okay, so first thing we're going to do is mod is equal to power of 10 to the 9 plus 7. Return res modulo mod, whatever res is. In a tiling, every square must be covered by a tile. Okay, two tilings are different if and only if there are 4 directionally adjacent cells on the board, such that exactly one of the tilings has both squares occupied by a tile. What's the search space? N is 1,000, so that means there can be an n squared solution, but not a 2 to the n solution. Okay, let me, oops. 1 second. Oops, I have a bottle of water for me with this. Amazing. Okay. Tiling, every square must be covered by a tile. Two tilings are different if and only if there are 4 directionally adjacent cells. What the heck? I see. So here n is equal to 3. A 2x n board. Okay. So you can either do this, that. Okay, so if you put one of these guys, you must put another one of these guys, right? So if you choose to put a Tromino, right? Yeah, there's no options, right? If you put a Tromino like this, then it's like you can't put a single domino here and a single. Oh, wait, maybe you can. You put this, then like a single domino here. Then like a Tromino here. Oh boy. Yeah, this is gonna be a little bit difficult. Oh boy. Yeah. Right. If it was 2x4, you could put this domino and a Tromino. Yeah, it's gonna be quite annoying actually. Maybe, wait, I think this is not a coincidence, right? What if you do like something like DP, where you keep track of the top index and the bottom index, right? If you put it this way, you moved the top index. Yeah, I think it's gonna be something like this, right? Def dp self 9 at j. Right, you have to be careful, right? If your j index is over here and your I index is over here, that means it's like there's stuff filled in, right? So you better be putting level 2 dominoes, right? I think it's gonna be something like that. Okay. Right. We're going to here we'll say n is equal to n. N is equal to south of n. If I greater or equal to n, equal to n, cert return. That's one way. Okay. Now, case 1, put a domino vertically. Case 2, put a domino horizontally. Case 3, put a tromino with R shape. Case 4, put a tromino with L shape. Right? This looks like an R. This looks like an L. Okay. For each one, so we have to think about each one if it's possible or not, right? So here we'll say case 1 is equal to float is equal to 0. Case 2 is equal to 0. Case 3 is equal to 0. Case 4 is equal to 0. Return case 1 plus case 2 plus case 3 plus case 4. Right? Press B equal to self.dp 0, 0. Right. Have a little bit more Greek yogurt here. Sweets. Money and I just came from a few-hour hike. That was pretty nice. That was pretty cool. So we're pretty famished for water. Okay. Yeah, we have to denote if these are possible. I can only put a domino vertically if is possible only possible if I are the same as otherwise there's a collision. If I is equal to j, case 1 is equal to you fix the domino vertically and then you count how many possible ways there are. So this will just be self.dp. Oh yeah, here we're returning 1. So this will be I plus 1 and j plus 1. Case 2, put a domino horizontally. Insert case 1 is greater than 0. So if we want to put a domino horizontally like this, there better be space, right? Now the only thing is you gotta think about Tromino, right? Because when you put a Tromino, my guess is to do return 1 if and only if I equals n and j equals n, maybe. Yeah, because we want to go through cases where it's invalid, right? We must fill in everything exactly. So if I do something like this, it just means that my I pointer gets shifted by 2 and this guy gets shifted by 1, right? Here we cannot put something vertically, so we have that case handled, right? If I doesn't equal j, then we can't put something vertically. But there should never be a problem with putting something horizontally. I don't think there's ever a problem. There should never a problem a domino horizontally. Um, put a domino horizontally, either the top or the bottom. When doing so, we must ensure we're not going out of bounds, i.e. j less or equal to n. Either top or bottom. If I plus 2 less or equal to n, then case 2 plus or equal to self.dp from I plus 2 j. If j plus 2 is less or equal to n, case 2 plus or equal to dp of I j plus 2. Put a domino with an R shape. If I plus 2 less or equal to n, then we'll say case 3 is equal to self.dp with I plus 2 and j plus 1. If j plus 2 is less or equal to n, and let's grab that. Then we'll say case 4 is equal to self with I plus 1 and j plus 2. So like this. Yeah, so this is an invalid assert. So first of all, let's try to return 1. Yeah. So return I is equal to n and j is equal to n. Really now? Okay. Interesting. I less than n and j less than n. Okay. Something like this. Okay, my bad. Really now? Okay. Huh. The North shape. Yeah, when can you do this? Yeah, if equals j and if I equals j, I guess, and this, right? Okay, yeah, that's accepted. Yeah, I can't make the verticals interfere with one another. So that's one thing. So do we fail a test case or do we pass every test case is the question, right? Wrong answer almost immediately. Holy crap, okay. Is our solution very slow? No. Okay. Okay, sweet. Okay. All right, n equals 2. The answer is this. All right. Yeah. So the point is we don't want to allow Tromino or Domino, whatever the heck. Yeah, Domino horizontally is the only one that's not going to need that case. Interesting. So which cases get caught? It's only I is equal to n cases. So really there should be I is equal to 2. You could have 2, 2. You could have 2, 2. That's really it, right? We just don't want to allow any Tromino stuff. Right. Holy crap, I have to use the restroom pretty badly. Oh boy. Okay. How do I do this? Right. Okay. Yeah, it was correctly initializing everything to zeros. This is a 3A. It would be nice if I can see which ones are the 3s I'm making. Let me think. MSI. Should this be like 1s instead? No. We're gonna say that. J and self.memo. Return self.memo of I, J. Is equal to this self.memo of I, J equals res, return res. Right. Printf string self.memo equals sweets. Bring my brightness up. Wow, okay. 0, 0. Okay, let's see. This is untrue. This is untrue. Untrue. Y is equal to J, sure. I is less than that, less than that. And yes, you can put a domino vertically. it's like, how many ways can you do that? This should give you 1. Print f string case 1 equals. The very first case 1 should just give 1. Yeah. Yeah, sure. Case 2. There's the 1, 1, and there's a 0, 0. 5 plus 2 is greater less than or equal to n. Not sure. Oh, I see. Oh, I see. These are being counted as different solutions. So, if I plus 2 less than or equal to n and j plus 2 less than or equal to n, then case 2 minus or equal self.dp of I plus 2, j plus 2. Do not double count. Is that it? Okay, here it doesn't like that. Right, the case where it's like you put 1 on the top and you put 1 on the bottom. If you do both of them, then you should definitely undo that. Okay. Now this guy is not chilling. Wait. If you put a horizontal domino, no, not forced to, right? Because if you put a horizontal domino and they were only like 1 apart, okay. Yeah, because just really should just include themselves. Like this should be completely fine here. Because this should have the case of adding j as a lower domino, this one adding I as a horizontal domino, so then it's like you don't want to double count, right? Like that's what I would expect. N minus 1 minus j plus 1 is how many there are remaining. So yeah, you'd want that to be even. So these should be okay, right? Right, if one of them is done, then all you can do is put horizontal dominoes on one of the sides. Okay. If I is equal to j, you can always put a vertical domino. That one cannot be wrong. That's this one. Now, what's the case when you might not put a? It's if you had a like like an R shape, you can put a horizontal domino right below it, and then you can fill it back in with an L shape. So there are definitely ways. There are definitely ways. Yeah, for these, you want to put a tromino, part of it is vertical, right? So you must be that I is equal to j. I is equal to j. Yeah, like this all just makes sense to me. This should be completely enough. So I guess it's this that's the bit of a weird one. Like this should be just enough. From 1 and 1, yeah, there's just two solutions, which is just n equals 2. This could also maybe be solved recursively, right? There's only like so many shapes you can make. You can put a vertical domino and then solve the problem for n minus 1, right? Yeah. When you put these guys, it gets spicy, right? Because then it's like you could put a lower domino, you could fill it this way, you could put one of these immediately, you could put a crap load of those dominoes. Yeah, the trominoes make it so you can't really solve it in that way of nice recursion. Something like this should just be bloody perfect, man. I don't get it. Because you get rid of the double counting element. Put one here. So however many solutions I could do. One of which is like, oh, put this guy here. And it's like, this how many solutions? The other one's like this, oh, and then there's that many solutions. Yeah, 2, 0. Says there's only one way. Correct. 0, 2. There's only one way. Just put one here and there we go. That's correct. When you have both, right? The point is there's only one way when you put things horizontally. So when you put these guys, then yeah, you can only put a vertical domino. At 1, 1, right you're here, it says, at 1, 1 it says there's two ways. One way is that, one way is this. Sure. 2, 0, 0, 2 is good. 2, 1 says there's 0. 1, 2, it says there's 0. Okay, so what's wrong here is our trominoes. Okay. At 2, 1, I doesn't have to equal j. Alright? Because it's about fitting in where, yeah. If I put an R shape, if I put in an R shape, wait, let me think about this. It could be that if my I and j are here, then yeah. Now my I is here, now my j is here. Yeah, so I can put, oh, there's also reverse L. Wait, there's 4 shapes here. Case 5, put a Tromino with reverse R shape. That's my mistake. Plus case 5. Yeah, here I'm not doing this incorrectly. Plus case 6. Yeah, these purple shapes are other Trominos I didn't consider. If reverse R, I need my I to be here, my j to be here, right? If I plus 1 is equal to j, if I is equal to j minus 1, then I can put it. Case 4, right? If this is my I and this is my j, so j minus 1, and my j gets incremented by 1, my I goes 1, 2. Self.dp with I plus 2, j plus 1. Case 5, sorry. Case 6, put a Tromino with reverse L shape. 6 is equal to 0 if, okay, I need this to be my I and this to be my j. If I minus 1 is equal to j plus 1, then case 6 is equal to self.dp of my I gets moved to 1, my j plus 2. What about something like this? Yeah, okay, submit. Upper limit exceed. Yeah, boy. Yeah, boy. That's what we like to see. Hashtag paints. Get this bad boy. See what happens. Yeah, boy. Yeah, boy. And there we go. Completion streak 293 days. Consistency is key. See ya tomorrow. And holy crap, 10,000 ms is 10 seconds. Yeah, a little slower than the 0 ms. Okay, I guess it doesn't like this maybe. Maybe I can just put a hashtag beautiful cache decorator. Oh, probably because I should be moduloing, right? Self.mod is equal to mod res modulo self.mod. Yeah, okay, so cache is worse. Yeah, so let me so this is fine. case 2 to mod is equal to self.mod. This shall return something modded. Equals 0 for case in case 1, case 2, case 3, case 4, case 5, case 6, res equals res plus case modulo mods. Yeah, it's still a little slow, eh? TLE now, really? Wow. It'll just be this and return 1. Here we won't put in an assert, we'll just return this. Here we won't put in an assert, we'll just return that. Here that's just implicitly true. You'll say I plus 2 comma j plus self dp of I comma j plus 2 minus self dot dp of plus 2 j plus 2, and if I plus 2 less or equal to n, case 2 is equal to this, j plus 2 less or equal to n, case 2 just equals that. That's one way of minimizing damage. Case 2 modulo equal mods. Right. Yeah, this is a really slow solution then. Wow. I mean, like, I really blew it out of the water in terms of slowness. Alright, what if I just don't use self.memo? Then I have to be super slow, right? Or I guess people probably find like an O of n way of doing things. Yeah. I mean, I saw n is equal to 1000. I'm like, okay, I can do n squared time. And then I started thinking of dp. I was like, okay, this makes sense, right? I guess maybe it's like they do the n-1 thing where it's like, you know, there's only so many things you can do. I don't know. This is just what made sense to me, right? Okay. I mean, we can submit. It's just awfully slow, but at least we get a solution, right? Yeah, I guess that's just the case. Okay, it is what it is. Yeah, just a little bit, teeny bit slower than 0 ms, but you know, just does the job. 10,811 ms. Very, very, very fast. Okay, so nevertheless, as always in all my videos, I do a quick recap if I will solve a problem. For this one, you're going to notice that some people have 0 ms, 1 ms, 2 ms, 3 ms, 4 ms, 5 ms, 7 ms solutions for the most part. I think I'm around that range, you know, just, you know, this is just a number, O of 1, right? O of 1 ms. Forget about it. All right. So obviously, a very slow solution, but I came up with it because I saw in the constraints that n is less than or equal to 1,000, so I was like, okay, n squared is allowed. Dominoes and trominos, well, they're going to have a top row and a bottom row. So I can keep track of an index for where we are in the current top row, and an index for where we are in the current bottom row, right? Because how many possible indices are there in total? Where if in a 2 by n board, it's going to be, well, up to n indices in the top row and up to n indices in the bottom row. So how many pairs of indices are in total? Well, n squared, which is great because n is equal to 1,000, which means that n squared is equal to 10 to the 6, which is indeed a permissible amount of operations to do on LeetCode. So thumbs up for that. And that's exactly the approach that I went. So basically, I'm like, okay, we want to count how many possible ways can we fill a 2 by n board exactly no tile unseen, where the dominoes we have are not only normal dominoes, which can be horizontal or vertical, but also these tromino tiles. Now, one thing to keep in mind with the tromino tiles is I made the mistake of assuming they only have 2 orientations. One when they look like an R, like this orange shape, and one when they look like an L, like this orange shape. But there's 2 more, which is these purple shapes, which is a reverse L and reverse R, right? I call it R, R because this orange looks like an R, and L because this orange looks like an L, right? So this would be reverse L, this would be reverse R. So the trominos have 4 possible orientations, and the dominoes have 2 possible orientations. For the dominoes, it's just vertical and horizontal, and for the trominos, it's the 4 that I just discussed. So you'll see that in my DP function, I have 6 possible cases, and each of these is going to map to a different orientation, right? Either one of the 2 domino orientations or one of the 4 tromino orientations. So here, I just run self.dp of 0, 0. My DP function takes in an I and j. If I and j in self.memo, returns self.memo of I, j, yada, yada, yada. But the way it works is I'm going to start at indices 0, 0. And I'm going to keep asking myself, okay, how many different ways exist right now from my current I and j all the way up to the very end? Obviously, the original problem will be from 0, 0, i.e. you have nothing in the top row and nothing in the bottom row. How many combinations of dominoes can you put in whatever and count them all, right? So the way it works is like, okay, there's going to be 6 cases because there's 6 things that I can do, right? For my current ij, I can either put a vertical domino, I can put a horizontal domino, I can put an R-shaped tromino, an L-shaped tromino, a reverse R-shaped tromino, or a reverse L-shaped tromino, right? There's only 6 actions I can make at any given point in time. So that's exactly what I do. So here I say, okay, the end goal is to eventually get to the very end of the top row and the very end of the bottom row, right? So if I is greater or equal to n and j is less than or equal to n, well, here I'll make sure that in the other cases I never go above I equal to n and j equal to n, which is essentially when I is equal to n means it's like, okay, we filled all n slots in the top row, and j is equal to n means we filled all n slots in the bottom row. So in that case, just return 1 because there you go, you have just found one combination of dominoes and trominos that you can put in order to fill a 2 by n board, right? So this is just a base case. When you reach the very end, okay, if I and j is equal to n, then congratulations, you've reached the very end. So you've found one possible way of arranging the dominoes and trominos, right? Otherwise, if I is greater or equal to n, that means we finish the entire top row. So what can we do? Well, that means we can only put horizontal dominoes on the bottom row, right? Because everything else, right, a vertical domino would mean putting something on the top row, which you cannot, because if I is equal to n, right, then we're done with the top row. So we can't put anything on the top row. So we can't put a vertical domino. We can't put an R-shaped domino because it would have a vertical aspect. And we realize that every single domino has a vertical aspect, right? This orange R has this one. This orange L has this one. This purple reverse L has this one. And this purple reverse R has this one. So every single tromino has a vertical component, and a vertical domino is obviously itself a vertical component. So since I can't put anything in the top row, the only thing I can do, which is only going to affect the bottom row, is putting horizontal domino tiles, right? and which really only leaves me with one permutation, and so then I'll just return 1. But instead of returning just 1, I return n minus j modulo 2 is equal to 0. The point is that essentially I want to know, like, okay, since I'm done with the top row, can I keep putting dominoes on the bottom row until I get to the very end? Well, there's going to be two possible cases, right? Either I'm able to keep putting dominoes on the bottom row until I get to, the very end, right? Let's suppose, like, this is what our rows looks like, right? We have dominoes like this. Then it's like here I can put another length 2 domino, right? I could put another length 2 domino, right? And there we go. Okay, finally we fill the bottom row, right? But imagine there was just one more hashtag here, right? Then I could put one more length 2 domino, one more length 2 domino. Uh-oh, I've overexceeded myself, right? So when I get to this point, there's only one more space, but a domino takes up 2 when it's horizontal, so then I cannot add it. So here I'm just making sure that, like, okay, if I keep spamming the bottom with horizontal dominoes, do I get to the case where it's like, I reach the end exactly instead of overflowing by 1, right? Which is only true. Well, how many spaces are there left? It'll be, index n minus 1 is the last one, minus j plus 1. N minus 1 and plus 1 cancels each other out, so there's n minus j total slots for the bottom row. So it's like, okay, can this be divided by 2, right? Because the horizontal dominoes will be of length 2 each. So it's like, if this is divisible by 2, then you can indeed fill in the space with length 2 dominoes. So if modulo 2 is equal to 0, then there we go. Then we find, we return 1 because there is indeed a valid permutation. And same thing, if the bottom row is full, we just say, okay, can we keep spamming the top row with horizontal dominoes until we get to the end? If so, return 1, otherwise return 0, right? Same spiel. Okay, otherwise, if both I is less than n and both j is less than n, then that means there's still dominoes we gotta put in the top row, there's still dominoes we gotta put in the bottom row, right? And by domino, I mean, domino or tromino. So then there's the 6 possible cases I talked about, right? The very first one is you can put a domino vertically. Well, if you want to put a domino vertically, right, remember, since we want to fill in every single space, you can only do so when I and j is equal to the same, right? So when you can just put a domino like this, right? If my I is over here and my j, if my I is over here and my j is over here, right, then it's like, right, if my current orientation looks like this, right, 3 hashtags and 1, I cannot put, this is my current index I here, right, and this is my current index j. It doesn't make sense for me to put a vertical domino here, right? It's just not something I can do, right? So here maybe I can put like a horizontal domino here, right? And now all of a sudden, like here putting a vertical domino makes sense, right? So here's like, I put my vertical domino right here, right? So it just must mean that my I and j must be the same, otherwise I just cannot place a horizontal domino, right? So here I say case 1 is equal to 0. But if I is equal to j, that's like, okay, we can put a horizontal domino, a vertical domino, which would augment my index I pointer on the top row by 1 and the index j pointer on the bottom by 1, right? So that's why I do self.dp of I plus 1 and j plus 1. All right, case 2 is I put a domino horizontally. Now, I can either put it on the top or on the bottom, right? I can put either a horizontal domino on the top or a horizontal domino on the bottom, right? So keep in mind, like, if I put a domino on the top row, then it'll be like, my index I will get moved by 2, right? From I to I plus 2. So at every single point in time, you'll see, like, I'll do if I plus 2 is less than or equal to n, or if j plus 2 is less than or equal to n, then you can add a domino in the top or bottom corner, right? Let's start with these cases because they're a little bit easier. If I plus 2 is less than or equal to n, that means I can put a domino in the top row, right? So let me do exactly that. Case 2 will be self.dp of I plus 2 and j, right? However many possible cases there are from there, where it's like I essentially move my index I by 2 because I put a domino of length 2 in the top row, right? If j plus 2 is less than or equal to n, okay, then I can put, like, a domino of length 2 on the bottom row and count how many cases there are from there on, right? Otherwise, if I can put either a domino on the top row or domino on the bottom row, right? Then to cover both cases, what I do is like, okay, I'll do the cases where I put a domino on the top row, right? Which is I plus 2 here. The cases where I put a domino on the bottom row, right? But here I have to be careful not to overcount. So here I'm going to subtract by dp of I plus 2 and j plus 2. So why am I doing this? This is kind of like Venn diagrams, right? Like, probability of, like, A or B. It's like, that middle part that you got to remove. If that doesn't make sense, basically from self.dp of I plus 2 and j, and one of the options here will be to put a domino on the bottom, which means it'll compute self.dp of I plus 2 and j plus 2, right? Here, one of the options it can have is put a horizontal domino on the top, which means it'll count for self.dp of I plus 2, j plus 2, right? Which means that this is going to count the case of I plus 2 and j plus 2, and this is going to count the case of I plus 2 and j plus 2, right? Which means that the case from I plus 2 and j plus 2 is counted for twice. It's double counted, right? So here I'm removing that double count, right? Now, there could be more cases, right? Because here it's like maybe not necessarily they put a horizontal domino on the top, right? Like, who knows? But I'm accounting for the case I'm essentially accounting for this and be like, okay, you know, let's not do any overcounting. Actually, it might be that, like, you know, the only possible thing here, I bet you it actually still works if I just do case 2 is equal to self.dp of I plus 2, j plus 2, just because it's like, since I put a top down, actually, no, this will guaranteed fail. I can guarantee you this will fail. I can guarantee, I can guarantee you this will fail, just because there's cases where you can put, like, you know, a Tromino like this, then you can put a horizontal domino here, and then another Tromino, and that'll be, like, you know, completely valid type of situation. So we need to make sure that we count things in this way, where it's like we prevent double counting, right? So now if we run this again, everything will just be a-okay, which is a neat little trick that I learned, like, you know, from my Stabby 52 course at the University of Toronto Scarborough. Just like, you know, just with Venn diagrams, it's like, you know, if you have an overlapping thing with another one, it's like, you know, the middle part where they're overlapping, it's like, you know, it'll be counted for twice, so it's like remove that section so that it's only accounted for once, yada yada yada. Just a Venn diagram trick, right? But otherwise, this is just the case for putting dominoes horizontally, right? So here's, like, we know case 1, we're counting all the cases where we put a domino vertically at the very beginning, right? Otherwise, what about the cases where we choose to put a horizontal domino, right? And here I covered the case for the top and the bottom. Then case 3 is put a Tromino with an R shape, right? So something like this. Well, it must be that my I and J are the same here, because I'm going to have a vertical domino basically here, and there's going to be one more over here, so I'll just increment my I pointer by one more, right? So here's like case 3. I can only do so if I is equal to J, and obviously if I plus 2 is less than or equal to N, right? There's enough space to actually put the 2 here. It's kind of like putting a vertical domino and a horizontal domino at the same time here, right? So then case 3 will be just, you know, move I by 2 and J plus by 1, right? So it's like here I gets moved by 1, 2, and J just gets moved by 1, right? But again, I can only do it if, like, you know, I and J are the same, so I can actually put the vertical component here, and then it'll just be I will be augmented by 2. So I also check that I plus 2 is less than or equal to N, so that I don't go out of bounds, right? Then the rest of the very much the same, right? For this L shape, it's vertical here, so I must be equal to J. And, like, you know, I'm going to be putting 2 here, so it must be that J plus 2 is less than or equal to N, otherwise it'd be going out of bounds. Otherwise, case 4 is equal to, you know, I plus 1, J plus 2. Reverse R shape, right, reverse R shape is something like this. It's like, okay, it must be that, like, you know, the top row has enough space. So, oh, here I don't even check for that. Okay, wow. I guess I didn't need to. But the point is, if I put a reverse R shape, right, it must be that, well, we can't put in any gaps, right? We can't put any singular gaps. So it must be that wherever my I pointer is, right, for example, this orange, or at the beginning of this purple, right, it must be that my index I and my index J are, like, you know, exactly diagonal like this, where the index J is just one more than the I pointer, right? It must be my I pointer must be here, and my J pointer by here, or, like, you know, here, however way you think about it, right? But it must be that, like, you know, the current setup that we have looks something like this, right? It could be that we have, like, you know, way more stuff behind it, right? But the general end of how it must look like is kind of like, you know, if we separate things off here, it must be kind of like looking like an L shape here, right? Because we need to get to that point, so that we can put, like, you know, our reverse R shape here, right? Otherwise we can't. And note that, like, you know, something like this, it could be like, you know, you put a Tromino, right? Like here, let me call it T for Tromino, right? Let's put Tromino, and it could be that you do something like this, right? Which is what we expect. But maybe you put, you know, a horizontal domino here, but you put another horizontal domino here, right? But here you still have that L shape over here that you need in order to connect, so that you can put in your last Tromino, right? So this is exactly what I mean. It just means that, like, you know, the current ending of where we're at, it must be, like, you know, kind of like that L-like shape, so that we can match it with that ending R domino, because otherwise we'd have an empty gap that we do not want, right? So we can only put a reverse R shape if it is exactly the case that the I pointer is one less than the J pointer, right? So if I is equal to J minus 1, then and only then can we do a reverse R shape, right? So it'll be I plus 2 and J plus 1. And same thing for the reverse L. We can only do it if, like, you know, the current I pointer is one more than the J pointer, right? So if I is equal to J plus 1, then we can do I plus 1 and J plus 2, right? Now, basically what we've done is, like, okay, from a current IJ, we went over the case, like, okay, how many combinations exist where we put a vertical domino? What about when we put a horizontal domino? What about when we put a R-shaped tromino, an L-shaped tromino, a reverse R-shaped tromino, a reverse L-shaped tromino. And we counted how many permutations there and combinations there is for each. And for any of them, it could be 0, right? But otherwise, whatever it is, right? And then at the end, it's like, okay, what do we want? Well, we want the total number of ways from our current ij. So it'll be the total number of ways where we put a vertical domino right now, plus the number of ways where we put a horizontal domino, plus the number of ways if we choose to put any of the 4 domino shapes, and take all those and sum them together, right? So for each case, in case 1, case 2, case 3, case 4, case 5, case 6, I'm going to add that to res, right? So really here I could just say res is equal to case 1, plus case 2, plus case 3, plus case 4, plus case 5, plus case 6. And here I'll just do modulo mod for the sake of it. There we go. And then we'll see that this works, right? We're just modulo mod because these are going to be huge numbers. So that way it's like, I keep things reasonably small, because at the end we need a modulo result by mod anyways, right? So there we go. And this is a 9000 ms solution, which is obviously much lower than the 0 ms solutions, but it's just something that I knew would work within the constraints, so I just decided to do it. And there we go. We have a nice and working dynamic programming solution to this problem, where we just treat this as like, 2 rows, and we keep track of the current index that we're at in both the top row and bottom row, and just count the total number of combinations that we can do from there. And there we go. But otherwise, that's pretty much it for us to solve this problem. If you did find this video useful and enjoyable in any shape or form, I'd highly appreciate it if you left a like or a comment. Well, otherwise, I'll catch you next one. So till then, ciao, ciao, my friend. Bye-bye.